Hello student, last class we have discussed if we place a current carrying load inside uniform magnetic field, then the torque experienced by current carrying load, that is tau equal to NIAB cos theta, that is tau equal to the torque experienced by current carrying load, which is equal to NIAB cos theta, or tau equal to, right, that is M cross B, M vector cross B vector, because torque is a vector quantity, or another formula also we can write, that is tau equal to NIAB sin alpha. What is theta? The torque experienced by a current carrying load when placed in uniform magnetic field, then theta, what is theta? Theta is angle between the plane of the coil and magnetic field B vector. But what is alpha? Alpha is angle between area vector and magnetic field B vector. Clear? Last class we have discussed clearly. Now today we will go for a long question, that is moving coil galvanometer, or MCG, which is most important long question for your counseling examination. So first we have to use this concept. So this concept was discussed our previous class. Now we will go for what is moving coil galvanometer. Do you know what is galvanometer? What is voltmeter and what is galvanometer? Voltmeter means it measures voltage across a resistor. What is ammeter? Ammeter means we have to measure current through a circuit, so we have to use a ammeter. So what is galvanometer? Galvanometer means it is an electrical device which measure small amount of current when current flowing through the circuit, and it detect the direction of flow of current. Clear? So what is the meaning of galvanometer? Galvanometer means it is an electronic device which measures electric current, and that electric current is very small. That means this galvanometer used for measurement of milliammeter or milliampere current. Next, it is used to measure small amount of current like milliampere. Next, it detect the direction of flow of current. So this instrument is known as galvanometer. Clear? Okay. Next point, will come across the term or principle. Here the principle is used, that is when a current carrying load or coil placed in uniform magnetic field, it experience a torque, and the torque tau equal to NIAB cos theta. Clear? Which was discussed our previous class. What is tau? Clear? So by using this principle, here we have to find, or we have to determine the deflection of a moving coil galvanometer. So this is the principle which is used here. Next point, construction of galvanometer. Now we will go for construction of galvanometer. This is the construction of galvanometer. This is known as torsional head, torsional movable head, and this thread is known as phosphor bronze strip. Next, we have to use a concave mirror to detect the deflection of the scale, or to detect the deflection of pointer. Next, this coil or this phosphor bronze strip connected with a concave mirror which detect the deflection, and next there is connected or the coil which is wounded over a, suppose we have a soft iron core. This is soft iron core, and the coil which wounded over the soft iron core. This coil, this insulated coil, and this coil which is wounded over the soft iron core in this way. Clear? These coils are very tightly, and now this coil connected across a hair spring which is made up of phosphor bronze strip. This final situation, and total setup cover with a then the two magnet, or this magnet is known as horseshoe magnet. This is north pole, and here, and this is south pole of the horse magnet. Clear? And this total arrangement is covered with a non-metallic case to avoid external magnetic field or to avoid external disturbance. Clear? This is the construction of a moving coil galvanometer. First, we have to use a torsional head. Next, phosphor bronze strip which is connected with a concave mirror to detect the deflection of the coil. And say next, there is a soft iron core which is wounded over it, number of turns of the coil. And finally, this coil which is connected with a hair spring, and the spring which is made up of phosphor bronze strip. Clear? Okay, this is the construction of a moving coil galvanometer. This is north pole, and here one south pole. Clear? Okay. And this magnet is known as horseshoe magnet. Horseshoe magnet. Why horseshoe magnet we use? For moving coil galvanometer we discuss later, and we know the magnetic field lines always start from north pole and terminate on south pole, and This is the direction of magnetic field. Suppose we have a magnet like this. This is north pole and this is south pole. So all the magnetic lines are starting from north pole and terminate on south pole. This is the graphical representation of magnetic field lines. Clear? Okay, but here we deals with a horseshoe magnet or circular type magnet. Next will come across working or theory of galvanometer. Theory of galvanometer. Okay. What is first? We have to discuss what is soft iron core. Soft iron core means soft iron core. Iron core, here we use a soft iron core when the coil which is wound over it. Why we use here soft iron core? Because this soft iron core is a ferromagnetic substance. Ferromagnetic substance. We need here a large amount of magnetic field. We have to introduce here a large amount of magnetic field. So for large amount of magnetic field, here we have to choose a ferromagnetic substance, because ferromagnetic substance allow or pass all the magnetic lines which is coming nearer, and it allow all the magnetic lines, and magnetic lines are preferred to pass through ferromagnetic substance. That means the magnetic field strength inside the ferromagnetic substance is large. So here we use a soft iron core which is known as ferromagnetic substance. Clear? Okay. Next. Suppose here we use radial magnetic field. First, we have to discuss what is radial magnetic field. Radial magnetic field. So what is radial magnetic field? Suppose we have a horseshoe magnet. So the actual shape of horseshoe magnet like this. This is a horseshoe magnet like this, and this is one of the horseshoe magnet. If we observe from its top view, and then the magnet like this. Suppose we have a magnet, this is north pole and this is south pole. This magnet is like this. This magnet is like this, a cylinder. Clear? So this is north pole and this is south pole, and the cylindrical magnet is also known as horseshoe magnet. If we observe from its top view, then we will see top view of horseshoe magnet. This magnet like this magnet like this. One terminal, this is here north pole and this is here south pole. Clear? Okay. Suppose this is soft iron core and this is soft iron core. The coil which is wounded over it. In this way, the coil are wounded over the soft iron core, and this setup which is placed in between north pole and south pole of the horseshoe magnet. Clear? So if there is a cylindrical soft iron core, then the coil which is wounded over it like this. These are the number of turns which wounded over soft iron core like this. This is number of turn, and these turns are very close to each other. The area of each turn is same. That means these turns are very tightly to each other, and the coil which is insulated coil. So this is north pole and this is south pole, and this is soft iron core, and this is the number of turn which is pointed over a soft iron core. Clear? Now we have to draw magnetic lines. So this is a just like circle. If the magnet north pole and south pole is a straight line, then all the magnetic lines are, this is the graphical representation of magnetic lines. But in this case, the magnetic lines always start north pole and terminate on south pole. So this is the direction of magnetic lines. Clear? So this is the direction of magnetic lines. If we again draw it clearly, then this is south pole, and here the magnetic lines start, and this is like terminate here. Here also another magnetic line start, and this is the graphical representation of magnetic field lines. Graphical representation of magnetic field lines. Clear? Okay. We know two magnetic lines never cross each other. So the line which starting from north pole and terminate on south pole, but ferromagnetic substance try to attract and prefer to pass all the magnetic lines. So this is the direction, or this is the case, or this is the graphical representation of magnetic field lines in this way. Clear? The line which terminate at this point, so line which starting this point then terminate this point in this way, because two magnetic lines never cross each other. So these are the graphical representation of magnetic field lines. So these are graphical representation. Clear? And here, and this is the radius, and this is also radius, this is also radius. If you observe from its top view, then this is look like or just like a circle. So this field is known as radial magnetic field, because all the magnetic lines are along the radius. If this is radius, then here also magnetic line. If this is radius, and here also magnetic field lines. If this is radius, and here also magnetic field lines. So that's why the horseshoe magnet which produce a radial magnetic field. So this is the graphical representation of radial magnetic field. Okay. Now we come across. If we flow a current through the coil in this direction, suppose the current I flowing through the coil in this way, and this is the direction of flow of current through the coil. Clear? Okay. And the coil which is inside a horseshoe magnet, because it provides a large magnetic field. Why? If there is a strong magnetic field and this magnetic field is constant, if we place a current carrying lobe inside the strong magnetic field or constant magnetic field, then the current carrying coil, then the current carrying lobe which produce or which experience a torque, and here we have to find first that torque, and we know that is the torque experienced by a current carrying lobe when placed inside a uniform magnetic field, then tau equal to NIAB cos theta. What is N? N means number of turn over a soft iron core. What is A? What is I? Means current flowing through the coil or coil. Next, A means area of the coil or area of each turn. Here, area of each turn is constant because these turns are very close to each other. Next point, what is B? B means magnetic field strength, and this magnetic field which is radial magnetic field here. And what is theta? Theta is angle between plane of the coil and magnetic field strength B. Suppose this is soft iron core and the coil which is wounded over it. Clear? Okay. If we want to choose this is the direction of magnetic field B, because magnetic field lines are along the radius. If we choose this radius, then here also a magnetic field line. If we want to choose this is radius, then here also a magnetic field line, because here magnetic field lines are radial. So if this is a coil, this is a soft iron core and coil which is wounded over it, and this system and this coil and this turn which is inserted, which is inside a horseshoe magnet, north pole and south pole. Clear? So if this is turn, then this is the plane of the coil, because this is turn. If there is a number of turn, so it make a current carrying loop. And if this is a current carrying loop, then this is area of the loop. Clear? But in this case, if this is the direction of magnetic field, then this is the plane. So here the direction of magnetic field and the plane which make an angle theta equal to 0 degree. Clear? Okay. We can take another example. Suppose this is also a direction of magnetic field due to radial. This is direction of magnetic field B. Then if the coil turn like this, then this is also, if this is the turn over a soft iron core and this is the plane of the current carrying loop, then this is the direction of magnetic field, and here the plane of the coil, or here the plane of the loop are along the same line. That means theta is angle between plane of the loop and magnetic field. So here the theta is 0 degree, because the plane which is linear direction with magnetic field B. So here each and every point theta is 0 degree, because due to radial magnetic field each and every point theta is 0 degree. Clear? So when current flowing through the coil, the torque experienced by a current carrying loop inside uniform magnetic field, that is tau equal to NIAB cos theta. So here each and every point inside a horseshoe magnet, the plane of the coil and magnetic field is 0 degree. So tau due to current, which can be write, that is NIAB cos 0 degree, and we know the value of cos 0 equal to 1. So tau equal to NIAB. Clear? So this amount of torque experienced by a current carrying coil or current carrying loop when we place it inside a uniform magnetic field. So here the magnetic field is radial, so tau due to current carrying loop, which is equal to NIAB, equation 1. Clear? Okay. Now this is north pole and this is south pole. You have to imagine it, and this is top view of horseshoe magnet. This is like cylindrical. In this way, this is horseshoe magnet, here north pole and here south pole. Clear? Okay. Now, if current flowing through the coil or current flowing through the wire, and this wire which make a closed loop inside a uniform magnetic field, and the magnetic field is radial, that means when current flowing through a rectangular coil or rectangular loop or any loop, then due to this current it affect a torque, it experience a torque. Clear? Suppose this is the direction of torque, then the coil which rotate inside a magnet, that means north pole and south pole, inside a strong magnetic field, and this coil which is rotate. Due to rotation of the coil inside uniform magnetic field or radial magnetic field, the phosphor bronze strip get twisted, because if this is here south pole and here north pole, if this coil which is rotated inside a horse so magnet, then the phosphor bronze tip which is connected to the coil, the phosphor bronze tip also gets twisted, and the lower part of the coil which is connected with a hairspring, if coil rotates inside a strong magnetic field, the phosphor bronze tip also get twisted, and at that time the hairspring get tight, because the hairspring also rotated in this way and it get tight respectively. Clear? Okay. After some time, okay, in this case, if we disconnect, if current flowing through the circuit is zero, if we disconnect to the circuit, then current flowing through the circuit is zero. But initial situation, when there is a current I flowing through the coil, then this is due to this current, the coil experience a torque, suppose in this direction, and due to this turning effect, the hairspring also get twisted and the hairspring also get tight. Now the current flowing through the circuit turn to be zero. Then the tight hairspring now try to regain its original position, because everybody or every particle want to try to remain its initial position. That means according to Newton's first law of motion, inertia position. So the hairspring which is tight when current flowing through the circuit, when current flowing through the coil is I, if current flowing through the circuit is zero, then the tight spring try to regain its original position. So the coil again rotate its opposite direction to regain its normal position. Clear? Okay. Now suppose we know this is now equal to NIAB. Suppose we have a spring which is fixed over a table. This is spring, and here the spring which is connected with a mass spring, and this is equilibrium position where net force acting on the body is zero. If we displace the particle, if we displace this mass due to external force through a displacement x from its mean position, after removal of this deforming force, then this block try to regain its initial position, but due to velocity, then it overshot its position, and after some time it oscillates above their mean position and come to rest. Why? Because everybody want to stay in their initial position or equilibrium position. So in this case, F is directly proportional to x, that means minus x. That means this is displacement. Here what is F? F is known as restoring force. F is known as restoring force. What is x? X means displacement from its equilibrium position or mean position. Why negative sign? Negative sign here indicate that the restoring force which develop inside the spring, which is opposite to the direction of displacement. If displacement in this direction, if extension of the spring in this direction, then restoring force develop inside the spring which is opposite to displacement. So negative sign here. And that force is known as restoring force. What is restoring force? Restoring force means which try to regain, which try to come the block to its initial position, and that force is known as restoring force. But here the displacement is linear displacement, and here the restoring force is linear force. But in this case, due to the rotation of coil, due to rotation of the lobe inside a strong magnetic field, the phosphor bronze tip get twisted. That means it makes some angle. So here After some time, the spring also get twisted and the spring also get tight. After some time, or after any equilibrium position, the restoring torque, or you can write first we have to find what is the torque or restoring torque. So when the spring get tight, when the spring which is rotated inside a strong magnetic field, then the spring also get rotated, and in this case we can write tau as restoring torque, which is directly proportional to phi. What is phi? Angle of twist. Phi means angle of twist, like F equal to minus kx, or F is directly proportional to x. Here this displacement is linear displacement and this force is linear force. Similarly, this displacement is angular displacement due to turning effect, and this force, here the force linear force, but here at a torque on the lobe. So you can write restoring torque, which is directly proportional to angle of twist. If angle of twist increase, then restoring torque develop in the phosphor bronze or hairspring, which also increase. If angle of twist decrease, then restoring torque develop in the phosphor bronze and hairspring also decrease. So you can write that is tau r restoring torque, which is directly proportional to phi. That means angle of twist. And this tau r restoring torque, which is equal to one constant quantity, constant into phi. What is restoring torque? Restoring torque is the type of torque developed in the phosphor bronze strip or hairspring, inside the hairspring, which always try to come back to its initial position, where net force acting on the spring is 0. That means it try to always come back its initial position when current flowing through the circuit is 0. So tau r equal to one constant into phi, and here we can write tau r equal to c into phi. So what is c? This is equation number 2. What is c? Here c is called, where c is proportionality constant. Proportionality constant, and it is known as torsional constant. Torsional constant, or you can write C equal to restoring torque per angle twist. Here restoring torque per angle of twist equal to C, which is constant quantity. That means if angle of twist increase, then restoring torque also increase. That means this is constant quantity. Clear? Okay. Next, we have two equations. That is equation 1 and equation 2. So what is equation 1 and equation 2? Equation 1, that is tau, which is developed if there is a coil or if there is a lobe inside uniform magnetic field, then tau equal to NIAD. Here theta is 0 for radial magnetic field, and this is equation 1, and tau r restoring torque, which is equal to C phi. This is equation 1. Clear? Okay. And here the I is the current flowing through the coil, and the term which is the coil which is rotate inside a radial magnetic field. Now, after some time, the restoring torque, which is equal to torque experienced by a coil inside the magnetic field, or the torque experienced by the rectangular lobe inside a uniform magnetic field B. So from this relation we can write tau equal to tau R. For equilibrium condition we can write here at equilibrium condition the torque experienced by rotating coil inside a uniform magnetic field which is equal to restoring torque. And if we use this value NIAB which is equal to C phi and this is I, so I can write C phi divided by NAB. Clear? Now from this relation we can write what is C? C is constant quantity. If number of turn constant, then area of the rectangular lobe is also constant. But here radial magnetic field is also constant. That means we can write I is directly proportional to angle of twist. So this is important relation, and here the important aim for the galvanometer, if deflection is large, if angle of twist is large, then current will be large. That means if we increase the current, then angle of twist of phosphor bronze strip also increase. Here where C by NAB is constant and this is termed as G. What is G? And G is also known as galvanometer constant. Galvanometer constant, and G is known as galvanometer constant. If the value of I, or we can write I equal to, which is equal to here CNAB, which is constant quantity, and it is G into phi. See another expression. If phi equal to 1 unit, if angle of twist equal to angle of twist equal to 1 unit, then current which is equal to numerically equal to galvanometer constant. Clear? So what the condition for which galvanometer constant will be equal to current flowing through circuit? When angle of twist equal to 1 unit. So next we will come across the what is the use of concave mirror, which is used for a moving coil galvanometer. And this is coil, and the coil which is placed inside a radial magnetic field. This is north pole and this is south pole. And if there is current I flowing through the coil, then the torque experienced by the coil which is inside the magnetic field. Actually what happens, if this is a rectangular coil and this coil which is inside a uniform magnetic field, suppose this is rectangular coil and of this soft iron core, the coil which is wounded over it. Clear? If magnetic field is strong, then it experiences a torque which rotates the coil inside the magnetic field or inside the horseshoe magnet like this. There connect a pointer. Actually, there connect a pointer over the or top of the rectangular coil or top of the coil or top of the loop, rectangular loop. When it rotates then the pointer also deflect and which determine on the concave mirror. So this is the use of concave mirror. Next will come the sensitivity of a galvanometer. What is sensitivity? Of a galvanometer. Sensitivity galvanometer means it gives large deflection. It gives large deflection for small current and voltage. For small current flowing through the circuit or for small voltage, the deflection of the current is very large. Suppose this is a coil and there is one pointer. This is horseshoe magnet, here north pole, and this point is south pole, and there is a scale in this way, and here this is the pointer. Here this is final scale or final reading of the scale, and this is the pointer. Suppose this is 0 reading here, this is the pointer. For small current, then the deflection will be very large. For small voltage, then the deflection is very large. So that's why the galvanometer is known as sensitivity of galvanometer, or this galvanometer is very sensitive for a small amount of voltage or for a small amount of current when flowing through the coil. Clear? So there are two types of sensitivity of galvanometer. First we have to discuss what is current sensitivity. Current sensitivity. Current sensitivity equal to, or it is defined as the angle of twist developed, or the angle of twist divided by a small amount of current flowing through the coil. That means current sensitivity can be write IS. IS means current sensitivity is defined as the ratio of angle twist per unit current flowing through the coil. That means phi by pi. Clear? But we know the value of I, which is equal to or NIAB, which is equal to C phi. That is I equal to C phi by NAB. If you use this value here, so phi by I equal to C phi divided by NAB, that is NAB. Here 1 pi cancel, which is equal to NAB by C. And this is current sensitivity can be write, that is NAB by C. Clear? Okay. Now we can increase the sensitivity of a galvanometer, or the factor which depends on sensitivity of galvanometer, or how can we increase the sensitivity of galvanometer? How can we make a good sensitive galvanometer? This is sensitivity of current. This sensitivity of current, which is IS equal to NAB by C. IS increase. That means current sensitivity of a galvanometer can be increased by increasing number of turn can be increased. If number of turn increase, then sensitivity of galvanometer increase. Next, if area increase, area of the coil. Suppose this is this is soft iron core, and here this is north pole, and here south pole. First, we have to increase the number of turn. If number of turn here increase, then sensitivity of current sensitivity of galvanometer increase. If area increase means we have to increase the area of this rectangular lobe. So if area increase, then sensitivity also increase. Next point, if magnetic field strength B also increase, then sensitivity of galvanometer or current sensitivity also increase. What is C? C means proportionality constant or known as torsional constant. If torsional constant decrease, then sensitivity or current sensitivity of galvanometer increase. So here we use phosphor bronze tip to decrease C, so that the current sensitivity of galvanometer increase. This is all about current sensitivity. Now we have to discuss. Now we will go for what is voltage sensitivity. Similarly, second test, voltage sensitivity. Suppose voltage sensitivity Vs, and voltage sensitivity can be defined as the angle of twist for voltage supply or voltage apply across the clear. So phi equal to V. Vs equal to phi by V. What we know according to Ohm's law, from Ohm's law, V equal to I into R. What is I? I equal to C phi divided by NAB into R. Clear? This is the value of I, and then V can be write in terms of C. This is the value. So if we replace or if we use this value here, then V equal to C phi by NAB, it is NAB into R. Clear? 1 pi cancel. So Vs equal to NAB divided by CR. Clear? Okay. How can we increase voltage sensitivity? So, if we want to increase voltage sensitivity of a galvanometer, then we have to increase area. If we increase number of turn of a galvanometer, then can we increase the voltage sensitivity? If number of turn of the coil increase, can we increase voltage sensitivity of a galvanometer? No, because if this soft iron core and if number of turns increase, then the length of the coil, then the length, if we stretch in this way, then total length of the coil also increase. We know resistance of the coil which is directly proportional to L. That means if number of turn increase, then length of the coil also increase. If length of the coil increase, then resistance of the coil increase. Suppose number of turn increase, that is 2N, then resistance of the coil also increase 2R. So if we use here, that is 2N A into B divided by C into 2R. 2 cancel, then NAB by C into R. This is important short question. If we increase number of turn of the coil, then can we increase current sensitivity? Yes. Can we increase voltage sensitivity? No. Because if number of turn of the coil increase, then length of the turn increase. If length of the turn increase, then resistance of the turn increase. So 2 cancel. This is example 2 cancel. The same thing NAB by C into R. So what is the condition for which voltage sensitivity of a galvanometer can be increased? That means if you want to increase voltage sensitivity, then you have to increase area, we have to increase area, magnetic field, but we have to decrease the value of C. So here we have to use phosphor bronze piece, phosphor bronze strip, which decrease the constant factor. So this is all about what is moving coil galvanometer, what is principle of moving coil galvanometer, what is working, what is construction, what is theory, and next what is sensitivity of galvanometer. This is all about a moving coil